In this lecture, we look at irreversible processes and a concept known as entropy. Some things reverse. So if you're looking at a bouncing ball, you may not be surprised if it falls, hits the floor, and bounces back up to about the same place over and over again. But others don't, for sure. For example, as you burn a candle, you don't expect it to suddenly turn around and burn back up. So energy can be conserved, but for both of these, but whether the bouncing ball or for the candle, but something is not. And the thing that's not being conserved is known as entropy. For an irreversible process in a closed system, the entropy S of the system always increases. So this is a definition of what entropy is. So it says that the change in entropy of a system, SF minus SI, is an integral of the change of dq over T. So entropy depends on the heat transferred and the temperature at which it is transferred. So it includes both of these ideas, heat and the temperature. If the changes in temperature are small, so we're not changing the temperature by quite a bit, then this is approximately equal to the heat divided by the average temperature. There's also an entropy for a reversible process. Consider an isothermal process. In this case, we have the change in entropy is equal to this integral from the initial state to the final state of dq over T. Well, it's an isothermal process, so we can pull out the 1 over T. So then we're just integrating from the initial to final state, and that's just the change in heat. So that's just equal to Q over the temperature. And we see that if heat goes into the system, then the change in S is greater than 0. If heat comes out of the system, the change in S is less than 0. Let's look at an example of entropy change in temperature. Water is heated from room temperature, 20 degrees C, to the boiling point, 100 degrees C. In which 10 degrees C interval is the entropy change the greatest? The temperature is not changing very much, so we can use the approximation that the change in entropy is equal to the heat divided by the average temperature. The heat is given by the mass times the molar specific heat times delta T. Delta S for going from 20 to 30 degrees is then approximately equal to the mass times the molar specific heat times delta T over the average temperature, which is those constants times 10 degrees K over 298 K, the average temperature. So we have a fraction of 10 over 298 times the mass times the molar specific heat. For the interval from 30 to 40 degrees C, we have a similar function or formula. We have the mass times the molar specific heat times the change in temperature over the average temperature. The numerator, the heat, is identical to the previous one, but the average temperature is now higher, 308 degrees K, so we end up with a fraction of 10 over 308 times the same constants of the mass and the molar specific heat. So we can figure out our answer right away, and the answer is that first interval from 20 to 30 degrees C, because as you go up higher in 10-degree intervals, the heat stays constant, but the average temperature gets larger. So the first interval has to have the greatest change in entropy. Let's look at another little example. We have 2 kilograms of ice at 0 melted until there's a mixture of 1 kilogram of water and 1 kilogram of ice. How much does the entropy change? Well, the temperature stays at 0 degrees C because you end up with a mixture of ice and water. So that we have delta S is equal to this integral from the initial to final of dq over temperature. Well, the temperature is constant, so we can just pull that out. And the integral then is just, this is equal to Q over T, so if it is isothermal process. So that we have the mass of water so we took 1 kilogram of ice and turned it into 1 kilogram of water, so it's the mass of the water, times the liquid heat of, times the heat of fusion, divided by the 273 K, which is the temperature of the water-ice mixture. Plugging in all the values, we end up with 1,219 joules per degree K. This is just a reminder that entropy depends on both energy and temperature.